Hello everyone, welcome to Civil Engineering Geeks. In today's lecture, we will first learn what is a force and a moment, and then let's discuss about types of loads that are possibly applied on a structure. Now, what is a force? It is a physical strength or a load that has been applied at a particular point or on an object. Here, it is very important that the force or a load is applied at a point. A force can be a pull or a push or simple load from any external body. In civil engineering, we define the pulling force as tensile force or a tension and the pushing force as compressive force or a compression. These forces have their units in newtons, kilonewtons, kips, pounds and in kgs. Next, we will see what is a moment. It is a rotational force which will be created by any force that is applied on an object by rotating from where the force is applied to where the moment is required. Basically, moment equal to force times its perpendicular distance. Let's see this with an example. Suppose I have a wooden slab on which a force F has been applied at point A. Now we are going to find the moment that will be created by this force at point B. So the moment at B due to this force at A will be equal to force times its perpendicular distance, that is L. The length is L here. Now we can also write the unit of the moment from this. Say the unit of the force is in Newton and the length is in mm. Therefore, the unit of the moment is going to be Newton mm. And finally, we will move on to discussing about the types of loads. There are different forms or types of loads that are available and are possibly applied on any structure in reality. We will now see the three most important and frequently used load cases. Beginning with the point load, these loads are also called as concentrated loads, which acts at a point. These types of loads are seen in tension and in compression members in practical cases, but theoretically it can be applied on any member or element on the structure. It can be applied on beams, columns, foundations and much more structural members of a structure or a building. Let me show you some real structures. The point loads or tension and compression occur mostly at the steel structural joints. The members connected to a steel structural joint may exhibit tensile force or a compressive force, which is a typical example for the point loads. Apart from this, as I said earlier, it can be applied to any members of a structure theoretically to just simplify the complex load cases for the analysis of that member. We will see this in detail later in this lecture. Point loads have their units in newtons, kilonewtons, kips, pounds and in kg. It's same like a force. Next we have uniformly distributed loads. They are also called as line loads or rectangular loads. These uniformly distributed loads are the most seen loads in all kinds of structures, from a small residential building to long flyovers and skyscrapers. As the name indicates, these loads have uniform load for the entire span of the load case. Note that it is spread over the span of the load case, not the entire length of the member or an element. UDLs can be loaded throughout the member length, but it is not the only case. It can also be loaded for a particular length of the member. For example, let's say we have a beam or a member. In this, the UDL load is applied over the entire span of the beam. Therefore, the length of the UDL load case and the length of the beam are same here. And UDL loads are denoted as load, that is W per meter is the length, how long it is acting, and like I said, the load W is uniform. It won't increase or decrease in the span of the load case. We can also have something like the UDL is only applied at a part of the beam. Say it is only acting at the middle portion of the beam for a length A. Here, length of the beam and the length of the load case are not equal. The length of the load case is A, where the length of the beam is L, which is much more than A. Now let's see how to convert this UDL into a point load for simplicity. You can simply multiply the magnitude of the UDL with its length. For the first example, it will be W per meter times length L, which is also in meters, so meter gets cancelled out and we will get WL in the unit of newtons or kilonewtons, whatever it may be, in the unit of point load. And the big doubt here is where we will place this converted point load. It will be acting at the CG, the center of gravity of the load case. That is, for the first example, it is going to be L by 2 distance from either end. And for the second example, it is going to be A by 2 distance, right? Yeah, and the magnitude of the converted point load will be W times A. Great. Let's move on to our next load case. It is called gradually varying load. Unlike uniformly distributed load, these types of loads don't have uniform magnitude. Instead, the magnitude varies gradually or linearly for its entire length. Let's see few examples for this load case. In the first one, the load is gradually increasing from 0 magnitude at the left end to the maximum magnitude, that is W per meter, at the right end. These types of loads are called as triangular loads. But in the next example, the load case is having a minimum magnitude at one end. It is not 0 there, it is having some magnitude, and it's gradually increasing to have the maximum magnitude at the other end. These types of loads are called as trapezium loads, and these two types comes under gradually varying load. And we can also convert this gradually varying load to a point load by simply finding its area. That is, for a triangular load, it is going to be half times its base into its height, right? That is half times W times L. L is nothing but the base, its length, and W is nothing but the height or its magnitude. And this will act again at the CG of the load case, which is 1/3 of L from the maximum magnitude side and 2/3 of L from the 0 end for a triangle. Similarly, for trapezium, it is going to be the area of the trapezium for the point load, and it is going to act at the CG of the trapezium. If you think it's difficult to remember the CG of the trapezium, then it's totally fine. You will always have another way. You can split the trapezium into a triangular and a rectangular load. Now you know the area and the CG of these loads. You will get 2 point loads, one for triangular load and one for rectangular load. And the final load will be the addition of these two. Let me show you how it's going to work. Let 1 be the converter point load for the triangular part of the load, and it is going to act at the CG, that is nothing but 1/3 of L from the maximum end. And 2 be the converted point load for the rectangular part of the load, and it is going to act at the CG as well, and that is nothing but L by 2 distance. Now the total converter point load for trapezium load case will be the addition of point loads 1 and 2. Okay, now where will we find these kind of loads on real time? These loads are a bit complicated and will be found in complicated structures. The structures like dams and retaining walls. Let's see one example. Suppose we have a dam which is holding an amount of water on one side of it. Have any one of us thought how the external load developed by the water is acting on the dam surface? No, right? It acts horizontally in the uniformly varying manner. Why? Let me tell you. What's the weight of the water at the top surface? It is 0. And what's the weight of the water at the bottom surface? It will be the cumulative and the maximum, correct? Yeah. Which will give us the triangular pattern. That is nothing but uniformly varying load. Great. Since we have discussed about the important load cases in detail, let me break out the concept behind how the load gets transferred in a structure to the foundation before ending this lecture. Here, we are going to consider only the gravity loads, that is nothing but dead load and the live load. Okay. Starting from the top of this building, we have a slab or roof. The dead load of this slab and the considered live load from the Indian Standard Code will be acting all over the slab. From here, we will have to split these loads and transfer them to the beams beneath the slab. The loads are split in 4 parts like this, and each part is given to one beam. Now, a beam is carrying one part of the slab load plus the dead load of the beam, correct? Likewise, all other beams carry a part of slab's load plus their own self-weight. Now, the loads from the beams has to be transferred to the columns that are holding the beams in the nature of reactions. We will solve the beams, get the reactions and apply those reactions as a compressive load to the columns. Great. Now coming to the next slab and the columns on the top floor are interconnected, that is monolithically connected with the ground floor columns. So the columns on the first floor is going to transfer the loads coming on to them directly to the ground floor columns. In addition to that, the ground floor columns are going to take up the loads from the slabs and the beams on that level as well. So from this, you can understand that the columns at the bottom levels are to be built stronger comparatively to the columns on the higher level. And finally, from this ground floor columns, the loads are transferred to the footings or foundation, and from foundation to the ground, that is nothing but the earth. So this is how the load gets transferred from the top of the building to the ground, that is earth. Okay, let's do a quick recap on the load transfer mechanism. At first, we divided the slab and transfer each part of the load to the beams beneath it. The transferred load will act as a UDL to the beam. Then the load is converted as support reactions of the beam and transferred to the columns as compressive forces. Finally, the loads are transferred from column to the ground through footing or foundation. Thanks for watching the video. Appreciate all the support. If you think the video was valuable, feel free to share them and do subscribe to get the notification on the upcoming videos.